Mm. It is everything clear. Good morning, everyone. Good morning, Uday. Yeah. Good morning, Jugal, Srinivas, Santosh, Rahul. Very good morning, every one of you. Lasya, good morning. Yeah, got it, got it. Yes, hopefully everyone will join now, one by one. Meanwhile, we will start the class. See, in today's class, we are going to draw shear force and bending moment diagrams for a cantilever beam for different cases, like when a beam is subjected to a point load, or beam is subjected to a uniformly distributed load, or uniformly varying load, or it may be a couple. So first, basic cases, when a point load is acting and when a UDL, uniformly distributed load, or varying load is acting, or couple is acting. For simple cases, how we are going to draw that shear force and bending moment diagram, we will see in this class. Okay. Then in practical applications or in problematic part, we will be given with a load combinations, which I already sent you in the WhatsApp group today morning. Likewise, questions we will solve in next class. That is the problem solving. So first, before that problem solving, what is the basics required for this shear force bending moment diagram? Exclusively today's class we will discuss about cantilever beam. On cantilever beam, when forces are acting and the forces, external forces are loads are acting, how we are going to draw that shear force and bending moment diagrams we will see in this class. Next classes we will go with simply supported and overhanging beams. Okay. So first, see cantilever beam. As we already discussed in last classes, cantilever beam means a beam which is fixed at one end and free at another end. So a beam which is satisfying support conditions like a fixed support and a free support, free end. Such beam is called cantilever beam. So on this cantilever beam, when we are loading with external loads or external forces, then how this beam is reacting and how we are going to draw that shear force and bending moment diagrams. So first I am having case 1, that is shear force diagram and bending moment diagram for a cantilever beam when a concentrated load is acting on the beam at end. Means, see here, I am considering a cantilever beam. I am taking it like AB. I am considering a cantilever beam AB of length L is subjected to a point load W at its end, free end. So at its free end, a load W, either newtons or kilonewtons of intensity, is acting on the cantilever beam. So now for this load, we need to find the shear force diagram and bending moment diagram. Shear force diagram and bending moment diagram is nothing but the shear force acting at each and every section, and the bending moment act at each and every section here. So right now we are considering only this load, and we are going to find this shear force and bending moment in the entire section. So first, to maintain the equilibrium condition, as we already discussed in last class, while writing a system of forces, or while writing system of forces for equilibrium equations, then we need to find we need to calculate, or we need to take both external loadings and as well as support reactions. So we have to find support reactions first of all. Whatever the shear force diagram, bending moment diagram, for whatever beam it is, either a cantilever beam or a simply supported beam, or it may be a overhanging beam or fixed beam, whatever the beam it may be, first we need to find support reactions. Then only the system is in equilibrium. See here, everything we are dealing with a static bodies. So the body is in rest and is in equilibrium. There is no disturbance in that body. That's why we need to take a consideration or assumption always like body is in equilibrium condition. So we need to satisfy that equilibrium equations also. To satisfy that equilibrium equation, now we have to take the support reactions. See, the support reactions means here we are having A. At this A, this is a fixed support. We already know at fixed supports, both translations in X direction and Y direction and rotation around A, all these three are restricted. So both translation and rotation and both translations and rotations are restricted here. So we are having reactions in all three. Let us see first, W is acting upwards. So an opposite reaction force will happen at A in upward direction with the same intensity of W to balance this force, as it is good. And horizontal, there are no horizontal forces, so there is no need of horizontal reaction also. So horizontal reaction is becoming zero. No need of horizontal reactions. Then moments. See, this load W, the load which is acting here on point A, I am taking point A here, right? So on point A, this load W will create a clockwise movement. See, if we take it like point A as a bolt, a small bolt, if I take it, then this entire beam is like a wrench. So I am twisting this bolt. Let us assume it like a point as A, right? So now I am applying force here, W, at a distance of L. Then what will happen? The wrench tries to rotate this point or bolt A. The same manner, at point A, this force will try to rotate in clockwise direction. See, this is downwards, and at a distance of length L it is acting. So the force will try to turn like this. In a clockwise direction it used to turn. So at point A, if we consider this, it will happen on point A like this in clockwise direction. So to overcome this, To overcome this clockwise rotation, a reaction force has to be developed at A. Since here rotation is also not allowed, fixed beams rotations are not allowed, that's why here we are having an anti-clockwise reactional rotation. Anti-clockwise reaction rotation is observed here. So it is having a magnitude of force into distance. Force is the W and distance is the L. So whenever we are going to calculate a moment for couples, we will take it as load into lever arm distance. Same I am taking here. So this anti-clockwise here, it is causing a moment of W into L. This is the action, W into L. So the same reaction has to be produced, that is W into L. So if we see it, it will be like this when we see a free body diagram. So if we see a free body diagram of AB, I am considering this beam AB, right? So I take free body diagram of AB. Here the load W is acting and the support reactions W and moment which is opposing the reaction moment WL is acting on the member. Yes, so this is for equilibrium condition and we kept it fine and square. Good. Then how we are going to find the shear force and bending moment in this section? So for that we already learned some points regarding drawing this shear force and bending moment diagrams. So first and foremost one, kindly consider either right hand side or left hand side of the member. So we need to take any one side. And we have to start. So here I am taking a cross section here, right? I am taking a cross section and I want to place this cross section on any one side. So for time being, first I am placing it here on the right hand side. Okay, on the right hand side I am starting the cross section. Then I need to verify the shear force and bending moment at all cross sections throughout the beam. So I will start at B, which is the right end. From here I will start verifying the shear force and bending moment in all the cross sections like this up to end A. Right. So here I considered from right hand side. So from right hand side when we are considering means we need to take the sign conventions for shear force and bending moment which we have taken or which we have assumed in our previous class. That is, if we are taking a shear force like this on a beam, right side force is acting upwards, means I will take this simple assumption, that is run, which is right upward negative. So when I am considering from right side, see here I have cross section, okay, at point A, I will take it like this. So right of this A, how these forces are acting, okay, shear force, to find the shear force we need to give some sign convention. So to this section, right of it W is acting and immediate right of it reaction W is acting. So first we need to consider these sign conventions. The simple terminology which I use to remember this sign convention is run. Always I'll keep it in mind like run. Okay, run, right upward negative. So right upward negative. So at the same time, if it is a negative, opposite to this one, which is left downward, this is also negative. So these two are a pair. And at the same time, another two opposite to this, that is right downward and left upward. These two are pair. So these two are positive. We need to remember this terminology while drawing this shear force and bending moment. And at the same time, we have to follow bending moment sign convention also. So on bending moment, if on right side it is creating a clockwise movement. See, this load W, just now we discussed, this load W is creating a clockwise movement. So such kind of clockwise movement, right side it is creating means what will happen to beam? This beam will try to bend like this from the original position. So it tries to bend down. That is nothing but a sagging is happening in the beam. Sorry, hogging. So if like that hogging is happening, then we can say it is a negative bending moment. And at the same time, if bending moment is happening in an anti-clockwise direction, on right hand side I am saying it is a positive one where sagging is happening. Simply remember like a smiley. So this is the half smiley and this is another half. So we'll get positive bending moments. And here we are having negative bending moments. So we need to remember these two and let us draw this shear force and bending moment diagram. See, I considered this one here. First, I had taken the cross section. I have taken the cross section here. If I take it like XX cross section, I considered at point B. That is a far end or free end, right? So at B, I have considered on right side. I am considering everything from right hand side. Okay, from right hand side I am considering. So that's why on right hand side nothing is there. So let us draw a baseline for AB. Okay, this is the baseline for AB. We are representing the beam in form of a line. So here on B, right hand side, exactly at the position of B, nothing is there. So it is simply 0 shear force. Then next, what I am taking, see, from here I am just moving the cross section, means I am taking a cross section, just immediate left, very small change, immediate left to the B. Immediate left to the B, I have considered the cross section, same XX. Then now what will happen on right hand side, there is a point load, right? It is of intensity on right hand side here. There is a point load of intensity W, which means right hand side downward. We know RUN, right hand side upward is negative, but right hand side downward is positive. So we got a positive value. Remember the third or fourth point, I don't know exactly. We have one point in the important points, that is whenever there is an action of point load or concentrated load, the shear force will suddenly increase or suddenly decrease. So at that point B, it is 0, but immediate left, if we have considered the section, then on right hand side there is an increase in load. So suddenly it increases to W. So we have shear force here. See, shear force at B increased to W. Right. Then from here I am moving towards A. Okay. From here when I am moving towards A, there is no change. So I came up to here. Right. Here I am taking the cross section from this B, immediate left of B to immediate right of A. There are no change. So the entire shear force diagram will go on a straight line. Then again, see, if I take immediate left of A, what will happen? The W shear force which is going to come here all along the line. Now an opposite force, okay, this is right downward, which is positive. So we have considered this positive W and we draw this one. Now we have right upward. See, I am taking the cross section here. The entire right part I am considering. Only right part. Don't bother about left part. Just leave that left part. Don't bother about it. Just right part I am considering. So here W is acting along this length. Now same magnitude, W is acting upward. So what will happen? Suddenly W and W will got cancelled and it will become 0. So see here, from here W value to, it will suddenly drop to 0 again. This is our shear force diagram. It is very simple. See, we have just calculated. Just remember the equation. Shear force, that is the summation of forces sigma V or sigma F. This is the summation of the forces or shear forces acting on a section either to the left hand side or to the right hand side. So I considered from right hand side here. Same if we consider from left hand side, whether we will get the same or not. Yes, we will get it exactly. Then only our valuation or our problem is correct. See, if I consider from right hand side, sorry, left hand side, if I consider, then here check it, we are having W, right? If I take the section, simply if I take the section here first, so what will happen? From left hand side, left hand upward, LUP, left hand upward is positive. So first from A, W will start. Then from here, it will go back to this point, which is B, just beside B. So up to this point, W will go on continue. Then it will come here and close. So either you are drawing from left hand side or you are drawing from right hand side, both are same. Both will give same answer. The only thing is we have to consider only one side. Right. I'll just elaborate it. Why? Because this is the first time I am taking it very slowly. From next drawing onwards, you have to understand this. Okay. Then see, next one, for bending moment. Okay, we got the shear force diagram. Now for bending moment diagram, what we need to do? Again, I am considering the same portion. See, if we have considered shear force from left hand side or right hand side, better conveniently take the bending moment also from left hand side or right hand side. It will be easy for you to calculate the things. So I am considering again from right hand side. So here we have to calculate bending moment values. Just remember one important point which we have discussed in very last point. Free ends of simply supported beam and fixed end of free end of cantilever beam and both ends of simply supported beam, bending moment is 0. Just we will verify this one. Check it here. Here we are having this point B, right? At this point from right hand side, I am considering there are no forces and there are no moments acting here. So if we take this figure like a baseline, if we have taken AB, then at B, on B, there are no forces and there are no moments. So it is 0. Okay, then next I am going to section somewhere here in between, that is XX. Okay, I am going to a section between somewhere here, that is XX, which is at a distance of X. Okay, so here this is at a distance of X. Now we need to find the bending moment value, right? So I am going to find M, that is the bending moment at XX. I will take it as mx, right? Mx equal to, see, at this point, if I consider this point as x, at this point bending moment is acting due to this force W only. From right hand side I am considering. Okay, so from right hand side I am considering, I need to take only W. So W, and at a distance of x it is acting. So the moment which is causing moment in x is force W into lever arm distance x, that is Wx. M at x is Wx. So here see, it is in the variable of linear variable of x, right? So this path, if we see this path, it is like straight line format, right? A equal to bx, which is representing a straight line format. So the path of the bending moment, will also follow a straight line method from b. So from b it will follow a straight line like this, where we got the value of w into x here. So like this, what I am doing, I am moving this cross section, or I am taking this cross section immediate right to A. This is our A support, right? So immediate right to A, I am taking this cross section. Then what will happen? The same thing. Here W is creating a clockwise movement. See why I am taking negative first of all. This W is creating clockwise movement. Movement is creating in this fashion, right? So at X it created a clockwise movement, and here at A also it is creating a clockwise movement. Remember, clockwise movement on right hand side, clockwise movement on sign convention, clockwise movement on right hand side will give hogging, means a beam tends to bend like this, crying type. So it is a negative one. That's why I consider downward, down the baseline, right? So if it is at A we have considered means this is the W into L. So the straight line will continue like this up to WL. So this is the point where we got bending moment as WL. So then next, see, this is for our easy understanding. I am writing this, or I am taking this section immediate left or immediate right. But actually at the section we have to take immediate means just adjacent. Now I am taking this cross section just left side of the support A. Then what will happen? Here we are having this W, and here we are having this W. See, if we are going to calculate these moments, okay, if we are going to calculate these moments, immediate left to A means A is also considered this time, right? So M at A will be equal to, first I am coming from right end, W into distance L, right? So W into L. This is actually acting downwards, and it is creating a clockwise movement. So we are having it as a minus WL, right? Then next here W is acting upward, and it is creating anti-clockwise movement. Anti-clockwise movement is positive. So W into, there is no distance. Actually it is lying on the point A itself. So it is 0. Then we are having a clockwise movement, support reaction. Support reaction we are having, that is W into L, right? So before coming to the right end, we are having minus WL. Yes, that is good. But immediately after A, if we just cross A, this movement will come here and it will make entire thing as 0. So obviously this is 0 and these two will get cancelled. We have 0. So from here, now the bending moment diagram will go to 0 baseline again. So this is our bending moment diagram. So if you see it in a simplified form, see, a cantilever beam subjected to a point load or concentrated load at its free end, then we found out the reactions at the supports first of all, then we draw shear force diagram and bending moment diagram. That is our first, very first and simple concept in shear force and bending moment diagrams, which is the drawing of shear force and bending moment for cantilever beam supported to point load. Okay, now I am going for case 2, that is shear force and bending moment diagram for cantilever beam with UDL over the entire span. So If you are having any doubts, just post it in the chat box. Okay, after last 5 minutes I'll give you replies, and everyone I'll answer you, don't worry. It may take time because since it is in presentation mode, I am unable to read your comments. At last 15 minutes, in last 15 minutes I'll take up your questions and I'll answer you. Okay, see, this time I am taking the same cantilever beam AB, okay, which is of length L, but loading condition. Previously, we had a point load W of a point load of intensity W is acting at the section, not at the section exactly, at the free end B. But this time, we are just making a modification like the entire beam is subjected to an uniformly distributed load. Entire beam is subjected to uniformly distributed load of intensity W Newton per meter. Right. So W newtons per meter length, W newtons are acting. This is the condition given. We need to find the shear force and bending moment at this section. So first I am taking the free body diagram. Okay. When I take this free body diagram, I want to convert it. Okay. Sometimes I may convert it, or if it is useful, if we convert this entire UDL as a point load. So if I convert it as a point load, then it will act like W into the total length is L, W into L newtons, and it will act at a distance of half of the length, that is L by 2. So this is the first one. The next, support reactions. We need to find the support reactions, right? So support reactions, the total force acting is W into L, right? W Newton per meter is acting. So if I convert it into a total point load, that is W into L, which is nothing but the total length. WL is acting, right? So that WL force only will react here as a reaction force, which is at A. Reaction force at A will be equal to W into L, right? And at the same time, this point load, this whatever the UDL we converted into point load, this will cause movement, right? This load or the entire load will cause movement in clockwise direction at point A. So at point A, this load tries to create a clockwise rotation. So an opposite force, an opposite reaction force and reaction moment has to be developed, right? So the force or the moment which is acting at A in action is given by load intensity into lever arm distance. This is L by 2 and this is also L by 2. So we can write it like W into L, that is the load, into L by 2, which is equal to W L square by 2. This is the action of the moment. So opposite reaction has to be appeared, that is also equal to W L square by 2. Okay, so if we simplify it, it will be like this. WL reaction force and WL square by 2 reaction moment are acting in the section. Now I want to find the shear force and bending moment diagrams. So first, for shear force diagram I am finding. For shear force diagram, I am considering the section over here, right hand. I am again taking from right hand side to left hand side I am moving. So right hand to left hand I am moving. First I considered a section at B. Okay, I draw the baseline. Actually, first I will consider the baseline. On the baseline at B, shear force, since C, just to verify on right hand side, right hand side of this B, there are no loads, there is nothing. So obviously shear force is 0 here, right? Then next we have to move from B towards A. We have to move from B towards A. So I considered section somewhere. I considered a section somewhere here. Okay, like XX section, which is at a distance of X. It is at a distance of X from B. Right. So now if I want to find shear force at section XX, okay, I'll mention it like Fx, that will be equal to C. The total shear force acting right hand to the section XX. Okay, so to the right hand of the section XX, what is the shear force acting here? The load W Newton per meter is acting, UDL. So I want to convert it into a total force. So W Newton per meter is the load intensity and it is acting over a length of X. So it is acting Fx as W into X. See, this is also a variable of X. So it is a straight line path. It is a variable of X and it will follow the straight line. So from B to this section, shear force will come like this. It will increase like this, and this is the intensity of W into X. So in the same manner, this is the length X. If I go up to this point A, then what will happen? W into X will become W into L, which is nothing but overall load. So this is going to be here, and the intensity will be equal to W into L. Now immediate left to the section, if we considered, then what is happening here? This W into L is also acting upward. All these forces from right hand side downward it is acting. So from right hand side downward it is acting means it is a right RUN opposite. Right hand upward is positive, right hand downward is right hand upward is negative and right hand downward is positive. So we consider these positives. Then suddenly right hand upward is acting with same intensity. Then from here it will become 0. So this triangular form and the entire shape is our shear force diagram. Okay, this is the shear force diagram for a cantilever beam subjected to UDL over the entire span. Right. Similarly, now we need to find the bending moment diagram. We need to draw the bending moment diagram for this section. So again, I am taking the same AB. Remember here, entire second unit is like this only. We have to draw the shear force and bending moments with the different cases. And it is very important in near future, not in near future. Entire civil engineering future is depending on this one only, first of all. These are the basics. Right. So on B, we have considered the section. So right of B, nothing is there. That is 0. Okay, well, it is good. Next, I am going to the section, same as we discussed in shear force. So I am considering a section which is at a distance of X. It is good. I have considered this one. Okay. Now, what is the bending moment acting at this section? Right? If I consider this section as MX, I need to find bending moment at section X, that is MX. Okay, MX. See, the total force or the total load which is acting downward here. Okay, that is, we got it already, which is nothing but W into X. This is W Newton per meter and the distance is X. So it will act exactly at the center. That is W into X Newtons. Right. So, and it is acting at a distance. We need to find the lever arm distance, right? So it will act at a distance of X by 2. X by 2 here and X by 2 here. So on X, what is the moment acting? We need to find. So on X, Wx is causing a clockwise movement. Okay, which is acting downwards means it is causing a clockwise movement. On X, this is causing a clockwise movement. So this is hogging in nature, means bending the beam in downward direction. So we have to give negative direction of load intensity W into X into lever arm distance, that is x by 2. So we will get mx equal to wx square by 2. So this is our bending moment at any section. Bending moment at any section. Why? Because any section means I am taking this section xx. It may be 1 meter, 2 meter, 3 meter, 4 meter, 1.1, whatever it is. Any section in general equation bending moment, we will get it as wx square by 2. See, this is in the form of x square, which is in parabolic form. So that's why curve is also parabolic curve we will get. We will get a parabolic curve while drawing this bending moment diagram. So simply I'll move here. Now I am moving to left end, that is A. Okay, immediate right to the point A. Then what we have left here, the x, which is the distance, will become L, right? So M at A, bending moment at A will be equal to W L square by 2. In place of x we have taken L. Okay, and most important point we need to remember, this is minus negative value. Okay, since it is causing hogging. Sorry. Yes. So bending moment diagram will come like this. See, this is not a straight line. Here this is a parabolic curve. A curve should be there, right? Then immediately I am making this cross section from here, just moving just left to the section, just left to the point A. Okay, then what will happen? This movement, whatever the movement has generated here, we are having for this clockwise movement, anti-clockwise movement is acting at reaction. So bending moment diagram, it will go to 0 again. So this is the total bending moment diagram for a cantilever beam which is subjected to uniformly distributed load over the entire span. So the simplified figure will look like this: shear force diagram and bending moment diagram. So here we have to mention this first. This is a straight line and this is a parabolic curve. I'll give you a small remembrance for this parabolic curves and cubic parabola later. Okay. This is the shear force and bending moment diagram for what is that? Cantilever beam subjected to uniformly distributed load. Okay. The next we have uniformly varying load. So from here I am just moving a bit fast. Okay. So first I am taking this same free body diagram. Okay. And now what will happen? This free body diagram, if I consider like 0, okay, on AB, at B load intensity is 0 and at A it is W newtons, then it is increasing from 0 to W, right? So then of length L, we have this total loading value as the area of the triangle, right? So area of the triangle we will get as half into base L into height W. So WL by 2 is the total load which is acting at this centroid, right? So at centroid this load will act, which is equal to WL by 2, and L by 3 distance it will act from here, since it is a triangle, to L by 3 on that side. So with this we will get the support reactions like this: WL by 2, to oppose the WL by 2 it is acting over here, right? And moment, so WL by 2 into distance L by 3. So WL by 2 into L by 3, we will get WL square by 6 here. That is the opposite moment acting at the point for reaction moment. Okay, so if we consider this, now again I am taking, see, I am for my convenience and for our easy understanding, I am always considering from right hand side. Okay, throughout this second unit strength of materials, I just want to consider from right hand side itself for my easy convenience. Okay, you may take from left hand side also. Maybe you can take it from left hand or right hand. Just remember, you don't get confused in that one. That's it. So I am taking the baseline AB here. Okay, baseline I am taking AB at B. From B I am taking on right hand side. At first there is nothing here, so 0. Okay, let's move to the section over here, XX. Okay, which is at a distance of X. So we need to find the shear force on right hand side. On right hand side, what are the shear forces acting over here? Only we are having this triangular load. Okay, base is X, we don't know height, right? So this is W and this is 0. So we can take interpolation from similar triangles. For length L, we are having W. For X length, what we will have? W minus 0 by L into Ex. So we will get it as Wx by L. This value here, this is the height. This height value is Wx by L. Okay, so we have this Wx by L, and now we are going to find this area. Okay, area of that small triangle is half into base x into height Wx by L. So we'll get Wx square by 2L. So this is only our shear force. Shear force at Xx, Fx will be equal to Wx square by 2L. So see here, in shear force itself, we are having x square term this time. That is, the shear force curve will be a parabolic curve. So if we continue the same up to this point A, so next if I take the section here, XX at the section immediate right to the A, or on A, exactly on A, if we are taking immediate right, we are having WL square by 2L. So curve will be like this. Curve will come like this, and it is having the maximum value as WL square by 2L. Then immediate left, we have WL square by 2L. Okay, that which is nothing but LL got cancelled and WL by 2. Right, WL by 2 we have got here. The same WL by 2 is acting in a reaction force. So it will come to 0. So this is our shear force diagram, and the point, the point we have to remember here is the curve which is shown here is the parabolic curve. Okay, then next, if we go for bending moment diagram, see, bending moment diagram, again I am taking the AB section. Okay, AB baseline. Now I am considering the section XX. Since at B on right hand side nothing is there, okay, we will leave it and take the bending moment as 0. Fine. Now we have to consider XX we need to consider, and now this area, okay, which I already calculated, we got that area as Wx square by 2L, right? The one which we got it in our shear force. Here we got that Wx square by 2L. That is nothing but the area, total area we got here, Wx square by 2L, and it is acting at a distance of, since it is the X, centroidal distance is 1/3 of X. So it will act at a distance of X by 3. So now mx, moment at section xx will be equal to load, that is wx square by 2l into lever arm distance, that is x by 3. So it will be equal to w x cube by 6l. Okay, wx cube by 6l we will get. So this is the equation in terms of power 3, which will give the shape of cubic parabola. So we will get this curve in the form of a cubic parabola. So if we consider this same at this section A, not section, at the point A, if we consider the section, then the x will become L, right? So m at A will be equal to W L cube by 6L. That will be equal to W L square by 6, right? So curve will be like this. Here we are having W L square by 6 value. Then here at the point A, the same reaction moment of W L square by 6 is opposing. So it will become 0. This is the bending moment diagram we got. WL square by 6 is the maximum bending moment value we have. Okay, then at last we are having one simple case, that is shear force and bending moment diagram for a cantilever beam when a couple is acting. Okay, when a couple is acting, it is very easy. See, first for this couple, reaction couple is acting at the fixed end. Okay, that is good. Then any shear force is there acting, or any external load is acting on the member, vertical loads or normal loads are acting, nothing is acting. So nothing is acting means no reaction force. Nothing, reaction force in opposite direction, normal reaction force is nothing is there. Fine, we have only this couple and opposing reaction couple. So we'll get a figure like this. So if we want to draw a shear force diagram, draw a shear force diagram, no normal forces or no vertical forces on the beam. On vertical beam, no normal forces. So shear force diagram is just a baseline. Nothing is there. Nothing to draw also. So shear force diagram is just a baseline. When we see the bending moment, see bending moment, if I consider this point, the section B, okay, if I consider this section B, at section B, what is happening? A moment W Newton per meter is acting. That is a clockwise direction. So on right hand side, clockwise direction means it is a hogging kind. So we will have minus W Newton per meter force is acting, and it will continue up to here. Okay. And at the same, here if we take the cross section, to that minus W Newton meter moment, an opposite reaction moment is acting with same intensity. So it will become 0. So if you see the bending moment diagram, it will show like this only. We are having W Newton meter intensity, and it will go on continue from B to A, and it will wind up to 0 over here. So just we need to remember one important point from this is, whenever a beam is subjected to pure couple, okay, purely couple loads or couple moments, when it is subjected, then there is no shear force. See, shear force is purely vertical, not exactly vertical ankodani. It is purely normal force acting on the beam. Okay, normal force acting on the beam. That's why shear forces are developed in the member. So there are no normal forces means there is no chance of shearing it off. So no shear force will be there. When couple is only acting means no shear force will be altered. Only bending moment is getting altered. That's why here shear force diagram is completely 0, and we have bending moment diagram. Okay, that is for case 4. So we have just discussed with point load, a cantilever beam with point load, cantilever beam with uniformly distributed load, uniformly varying load, and with a couple. Okay, so this is our cases. See, in practical problems, when we are going to solve, we will take this kind of problems for our solutions. Okay, to solve the problems, and in JNTU questions also they may ask such kind of questions only. Okay, it is given with point loads, UDLs, UVLs all together. Sometimes it may be asked couple also. Till in previous R16 sessions up to R16 there are no couple forces, but in R18 they included couples also. So there may be a chance of asking couple too. Okay, so this is your this is today's class. Okay, I'll wind up here. If you are having any questions or any doubts, please feel free to ask. Just comment there in a chat box. I'll reply you. Uday Kiran, sir, case 1 bending moment diagram. Explain it, sir. Yes, case 1 bending moment diagram. See, we have to consider it like load into lever arm distance. Load into lever arm distance we have to consider. Wait, I'll show you. See here I am taking a section XX here. When I am taking a section XX here, then at section XX, what is the bending moment acting we are considering? Okay, I'll just go back. See. So at this section XX, on right hand side, whatever forces are acting, that forces will cause movement in the section XX. Same first we explained like a wrench. Okay, a point XX, that point XX, take it as a wrench or nut. Okay, take it as a nut, and the entire beam is acting as a wrench. Okay, the entire beam is twisting that X. So we are applying a force W over here, and it is twisting. It is twisting in the clockwise direction, right? So what is its magnitude? How we are finding it means W into its lever arm distance. Actually, it is in your first year mechanics. How we are going to find that moments? Okay, the same moment we are just I am explaining here. The load W into distance X. That's why Mx equal to W into load into lever arm distance or eccentricity. Load into eccentricity we will call it. Load into eccentricity will give couple. Load into eccentricity, load into lever arm distance will give couple. Load into eccentricity will give moment. Whatever we are talking, everything is same. The same here, load into distance. Load into distance will give you moment. So that is W into X. So here it is like A equal to Bx, which is in the form of a straight line. That's why from B to this X, bending moment carried out in a straight line format. That's why Wx, which is a straight line up to this point. Okay, and moreover, this is creating a clockwise movement. Okay, that load W is creating a clockwise movement on right hand side. Since it is creating a clockwise movement on right hand side, it is hogging. Okay, member is going to hog. That's why we take it as a negative bending moment. Since we already discussed it in sign conventions. Okay, in sign conventions previous video, just go through that previous video if you are having any doubt in sign conventions. The same sign conventions we are following here. Okay, next. Case 4 once again repeats. Case 4, yes. One second, I got struck, I think. See, in case 4, we are just having a bending moment. Okay, sorry, not bending. We are just having a couple or moment acting on a beam. Okay, so we are not having any vertical forces, normal forces antam. We are not having any vertical forces acting. So when we are going to find the support reactions, at support reactions, this upward reaction force Ra will be equal to 0. Why? Because there are no downward forces. Like we first horizontal A is also 0 since there are no horizontal forces. Okay, that's why we are not considering from first. This horizontal thrust we are not considering. Likewise, since there are no downward acting forces, we are not having this Ra also. Only we are having movement. Okay, if a force is there, this force will cause movement. Okay, rotation moment it is causing. But instead of this, what is given? Directly movement is given here. Okay, directly movement is given. So this movement is giving here also. A on A also the movement is acting. So this movement will give a reaction movement in the opposite direction. That is same magnitude W Newton meter. Okay, this directly movement is acting it at this point means no need to find again this length. We are not supposed to find this length. Moment at any point, if moment of W Newton per meter is acting at this point means here also act the same, here also act the same, and here also act the same. Same moment will carry out throughout the length. That's why we made it like action reaction. Okay, so action reaction, when we are drawing shear force diagram, nothing is there. Shear force diagram, when if you want to draw a shear force diagram, if I consider a cross section XX here, right, on left, on right hand side or left hand side, we need to get some point loads or we need to get some reactions, then only the shear force will be developed. Okay, movement or couple, how many of you know or don't know? I'll just tell you, whenever a couple movement are given, movement or couple, why we are calling means at the same point, both upward force and downward force are acting. Both the upward force and downward force are acting. This will cause movement. That's why we are calling it as movements. Okay, so upward and downward got rejected and it will become 0 over there. That's why normal forces are not there here. Only movement is acting. So shear force is 0. ఎందుకంటే మనకి ఇక్కడ we are not having any upward or downward forces. Then bending moment. See, bending moment, why we are taking it here at this point? Bending moment means W Newton per meter load is acting, which is causing clockwise movement. That clockwise movement will create hogging in the beam. Beam ni ఇలా bend చేయడానికి ట్రై చేస్తుంది. Clockwise movement, right? Hogging, it is creating hogging. That's why we have considered negative W Newton meter value. And from here onwards there are no other loads. So same W Newton per meter will continue up to cross section. If we consider here till the cross section considered here, all these the only W Newton per meter will carry out at all the sections. So it is continuing from here to here as a straight line, and here an opposing W Newton per meter is acting, so it become 0 again. This is the case 4. Yes. Anything? Anyone else? If anyone else, just let me know. Just for a second, I will give you the attendance link. So in case 3, shear force at A, WL/2 gives a straight line. Where do we represent that straight line in shear force diagram? Case 3. in case 3. We are having WL by 2. Yes, we are having WL by 2. See, up to this point, when we considered Mokshna, yes, Mokshna only asked this one, right? See, from here, when we are drawing this shear force diagram, okay, up to this point, shear force diagram is increased with the condition like W x square by 2L, sorry, 2 Wx square by 2L, which is Fx. Right click is happening. Fx equal to Wx square by 2L condition we have used at section XX. Okay, and we found the value, general equation. So it is a parabolic curve. We continued up to this point, which is immediate right to A. If we consider this point as A, immediate right means actually the section we are taking on X, immediate right to A. We have considered this point like X is equal to L. So W L square by 2L, which will give WL by 2 at this point. So next, if we move just immediate right, sorry, immediate left to the A, if we moved, then what will happen? Whatever the increase on shear force happened up to this point by using this generalized formula for this load, a sudden load is acting. Okay, that is a sudden reaction force is acting from downwards, right? So whenever a point load is acting, sudden drop or sudden increase in shear force will happen. The same thing happened here. From this point, suddenly shear force dropped to 0. Why? Because the intensity of this entire load will be equal to the reaction force. Okay, this is the entire intensity, half into, that is nothing but a half into L, that is base into X, that is WL by 2. Total loading of this triangle will bear by only opposite reaction at A. So this variation, this WL by 2 shear force variation, since the varying load, variation in shear force will vary from here to here in this fashion. That is a parabolic curve fashion. It is increasing. Parabolic curve, it increased, and it suddenly at that point, due to this point load, suddenly dropped and it became 0. Okay. Is it clear? Yes, if you are not having any doubts, just we will wind up the session. It is becoming 12. Yeah. Every one of you post your attendance. Actually, some of you missed it in last classes. It won't be calculated for your attendance. Probably next time in next class we will conduct in Teams again if it is working properly. Okay, for time being, just fill that Google form, not Google form exactly, Microsoft form. It will be taken as your attendance. shall we wind up right now? If you are not having any doubts, I'll close it. Yes. Okay. See you in next class. Bye.